Hi and welcome to another lesson in the physics video series. Today we're going to be discussing two things, free fall and vertical projectiles. We're going to take equations 3, 4, and 5 from the physics reference tables and we're going to apply them to the free fall situation. To clarify, free fall is anything that you hold and drop and let gravity just pull it to the ground, and vertical projectile is anything you just throw straight up into the air. Of course, when it gets to the top of its flight, it'll slow down and stop, and then it'll free fall to the bottom. So we'll start with free fall, and then we'll look at vertical projectile. All right, let's get started and set up the free fall initial conditions. What is an initial condition? Initial conditions are the way the variables start at the beginning of a problem. Here we have a high hill. We have a ball at a certain height called y max, which is the d variable, and it is about to fall. If we analyze each one of the 5 motion variables, VO, initial velocity, V final, final velocity, acceleration, displacement, and time, we can see that there are some initial conditions that are already set up in a free fall problem. For example, the initial speed of anything that's about to fall from rest is 0 meters per second. So that's a given. When this ball falls and hits the ground, even though it eventually comes to a rest, we are interested in the impact speed. VF is the speed at which the ball hits the ground, not the speed the ball comes to after it hits the ground. And of course, if something is falling down to the surface of the earth, its acceleration is equal to gravity, negative 9.8 meters per second squared, and the negative means down. The dy, the distance on the y-axis, equal to the letter y, it's so many meters above the ground, and the time it takes to hit the ground is called the free fall time. Let's apply these initial conditions to formulas 3, 4, and 5. If we take equation 3, VF equals VL plus AT, right off the reference tables, and we apply the initial conditions, the only two that apply here are the initial speed and gravity. We know that the initial speed of anything that free falls is 0, so therefore this term drops out of the equation, and the A for acceleration turns into a G for gravity. Some students feel more comfortable leaving it as an A and just substituting 9.8 when they do the problem. That's fine. But what does this formula in the red box mean? This is not a new formula. This is the same formula as the one in blue. This is a case-specific application of Formula 3, and it gives us information. It says that the final speed or the impact speed of the object is equal to the duration for which gravity acts on it as it falls. The speed of the object at any time since it was dropped. That's a very important consideration because the way the formula is written here in the red box encapsulates a concept. Okay, let's take a look at equation number 4. This is the displacement equation. D equals VOT plus 1/2 AT squared. This is the formula directly off the reference table. And what two initial conditions apply? An initial speed of anything that free falls is 0, and the A for acceleration becomes gravity. When I put these two initial conditions in the formula reduces to 1/2 GT squared. I changed the letter D to the letter Y so you know it's on the vertical axis. This becomes important later on when we deal with motion in 2 dimensions. Let's talk about the meaning of this formula. This formula has a very simple meaning. It says that the position of the object, that's the Y value, at any time since it was dropped can be calculated. So we now know how high above the ground the object will be after it has fallen for this much time, usually measured in seconds. Over here, we have a variation of this formula. This is the free fall time variation. This expression, y equals 1/2 GT squared, can be rearranged and solved for t. A little note, this negative sign here will cancel out with a value that you don't see right now, but whenever something falls, it's moving in the downward direction. So you have a negative y canceling with a negative 1/2. It's always easiest to ignore the negative when you're moving in the same direction as gravity. And so when I solve this equation for t, I multiply by 2, divide by g, take the square root, and you get this one right here, the free fall time. Y equals root 2y over g. I cannot state enough how important it is to recognize that the free fall time is based simply on how high an object is when it falls. It's also good to memorize this one, even though you can take equation 4, rearrange it, and solve. It's encapsulating a concept, and since this comes up so often, you should simply know it. T is equal to root 2i over g. And finally, let's talk about equation 5. This is the v squared formula. Now, what's interesting about the v squared formula, number 5, as opposed to equations 3 and 4, it has no time in it. Time has been factored out by algebraic means. So this is a formula that has displacement as its basis. So the final speed of an object squared equals the initial speed squared plus 2 times acceleration times distance. Now, in the case of free fall, initial speed is 0. A is gravity, and we get v squared equals 2gy. Again, there's a negative because the negative is attached to the gravity. But when an object is falling, which means that it's increasing its speed in the direction that it's falling, there's a negative there too. So that negative will cancel with that negative. Now this formula, v squared equals 2gy, can be solved for 2 variables. You can either leave it this way, and you could solve for v, and you get the impact speed as root 2gy, which means that you know how fast the object's going to strike the ground based how high it was released. But you could also solve for an object's height based on its impact speed by dividing by 2g. So y equals vf squared over 2g. If you knew the impact speed, you could find the height from which it fell. So in summary, we use equations 3, 4, and 5 with slight variations of initial conditions to create the formulas that work for freefall. And you could see them right here. Now be reminded that you do not have to create all of these variations every time you want to solve a problem. You just use formulas 3, 4, and 5 directly with the initial conditions put into the equation right from the beginning. Let's take a look at an example. Here's a typical freefall problem with many parts. A rock falls from a high cliff. Based on the information provided, answer the questions below, show all work, formula, solution, answer, and neglect friction. And here we would, of course, give you a height or an initial time. And let's look at the questions that would come down. How far is the rock fallen when its speed is so many meters per second? From how high did the rock fall if it took blank seconds to hit the ground? What is the impact speed of the rock as it strikes the ground? What would be the time to strike the ground if the rock has fallen from half its original height? And then complete the following graphical analysis. Fill in the table of freefall speeds, graphically analyze the information, graph the data, draw a best fit line, state the slope, write the equation of the line, and determine the area under the line for a 10-second interval. Let's work through this problem. So we know it's a free fall problem, and we know its initial speed is 0. We're going to choose a speed of 20 meters per second to be a reference speed. We know gravity is 9.8 meters per second squared, and we want to find or prove that the height from which it fell was 490 meters in a time of 10 seconds. Let's solve this problem step by step. How far is the rock fallen when its speed is 20 meters per second? Well, this is a very easy problem to solve using Formula 5. We know that the final speed will be 20 meters per second, and we know the initial speed is 0. We know gravity is g, 9.8. We plug those into the formula, and we get 20.41 meters. The next question, from how high did the rock fall if it took 10 seconds to hit the ground? So we've chosen 10 seconds, and of course, this is Formula 4. We solve it for distance, and we know that the initial speed was 0, so the first part of the formula drops out. We're left with 1/2 gt squared. Again, the negative will cancel because you're heading downward, and downward is negative, and the negative cancels with the negative, so it's 1/2 of gravity times 10 seconds squared, which gives you 490 meters of freefall. In question 3, they ask you, what is the impact speed of the rock as it strikes the ground? We know that the impact speed comes from Formula 5, and we solve for V final. Since the V0 is 0, it cancels out of the equation, and you're left with the square root of 2 times gravity times the height from which it fell. And we know that that was 490 meters times 2 times 9.8. Square root that, and you get 98 meters per second impact speed. In question number 4, it said what would be the time to strike the ground if the rock had fallen from half of its original height? So the original height, we cut that in half, and we know we solved equation 3 for t, and we get the square root of 2y over g. So that would be the square root of 2 times half of the original height divided by gravity, and that gave you 7.07 seconds to impact. And finally, what would be the impact speed if the rock had fallen from half its original height? Intuitively, you should realize that it would be a slower impact speed because you don't have enough height in the air to build up that speed due to the acceleration of gravity. We would solve equation 5 for v. V is the square root of 2 times g times the height from which it's fallen. And we know that the new height from which it's fallen is half of 490. And we get an impact speed of 69.3 meters per second. And here we have a graphical analysis question. Complete the following analysis. Fill in a table of free fall speeds and graphically analyze. Graph the data and draw the best fit line. State the slope, write the equation of the line, and determine the area under the line for the 10-second interval. Seems like a lot, but it's very easy. In the table we have 3 columns. The time column, which always goes on the x-axis, the speed column, which will go on a y-axis of one of the graphs, and a d column, which will go on the y-axis of the other graph. Speed is equal to g times t, and as you recall, we derived this from formula 3. 9.8 times 0, 9.8 times 1, times 2, etc. And then, of course, the d formula. D equals v0t plus 1/2 at squared. Since v0 is 0, it's just 1/2 at squared. Gravity is 9.8. 1/2 of that is 4.9 times 0 squared times 1 squared times 2 squared all the way down, and this is the distance it's fallen in these amount of times. Let's take a look at the graphs. And here is the graph of distance versus time, and it gives you a perfect parabola. Its formula is d equals 4.9 t squared. Remember that the coefficient in front of the t squared is half of the acceleration. 4.9 is half of 9.8, and that's a perfect parabola. And finally, we have the v versus t graph. T is on the bottom, v is on the y-axis, and we have a perfect line with a slope of 9.8 meters per second squared. V equals 9.8 t, so this says that the speed of the falling object will increase by 9.8 meters per second for every second that it falls. And lastly, if we were to take the area under this triangle, using the area formula of a triangle, 1/2 base times height, we see that we have a base of 10, a height of 98. 98 times 10 is 980. 1/2 of that is 490, and the area of this triangle is 490 meters, and that's the distance the object has fallen in 10 seconds. And there you have it. This concludes the lesson on free fall. We anticipated that we were going to talk about vertical projectile in this video, but we're going to cover that in the next video. I hope you enjoyed the lesson, and thank you for watching.